Hello, my dears. Here we will start Module 3 material. Module 3 will be covered in week 8, 9, and 10. The delivery plan, as you see here, will be covered in week 8, week 9, and week 10, where in this module we are going to go through the electrical indicating and testing instruments. We will start here by the main part of the indicating instrument, which called PMMC, or Permanent Magnet Moving Coil, or it's called by the creator of that part, which Dearson Oval. So we can call it Permanent Magnet Moving Coil or Dearson Oval. It's two names to the same thing. This is actually the basic element in any moving instrument. Moving instrument means moving meter, like voltmeter, ammeter, whatever kind of measuring elements need this basic element to show the movement, which indicating the value to be measured. In terms of PMMC construction, we will see it in the next slide, where mainly it depends on permanent magnet, and in the middle of it there is a movement or a moving coil, where the moving coil is going to take current from the measured value, and that current will generate magnetic field. The two magnetic field will interact to cause rotation. As you see here is the construction of the PMMC, where the construction of the PMMC include permanent magnet, as you see here, south and north, and inside there is a cylinder, where the cylinder having coil moved on it. Let me show you the coil. This is the coil actually. This is a coil, where in this coil the current from the external circuit will go to inside it. I mean, any current coming from external circuit will go inside until it reaches to the moving coil here. Now, when current flow in this moving coil is going to cause magnetic field. The magnetic field generated due to the current flowing in the coil will interact with the magnetic field created by the permanent magnet. Both of them are going to cause the deflection, or I can say force will be generated out of that. Due to the two magnetic field, force will be generated. There will be an upper spring, or we call it hair spring, at the top and hair spring at the bottom. These two springs are providing kind of opposite force to the original force. This is showing the construction from different point of view, where we are having the permanent magnet. This is the permanent magnet, this is the south, and this is the north. Here is the core, where this cylinder, and this dark is the coil. They are mounted on this beam. This one have the pointer attached to it. This is the pointer. To understand what we are doing here, actually this is the meter. Let's say the meter is having certain pointer against the scale. So the pointer is this pointer actually, and this piece here is what we call the Dearson oval, or the PMMC. In the principle of operation, mainly we are having three forces, clarifying or making the principle of operation clear. The three forces are starting by the deflection force, where the deflection force, it's the force generated due to the presence of two magnetic fields. One magnetic field coming from the permanent magnet, and the other magnetic field coming from the current flowing in the conductor. This is magnetic field and this is magnetic field. This magnetic field due to the current flowing in the conductor, beside the magnetic field in the or coming from the permanent magnet, they are going to cause kind of force. If you look at it here, you will find that the magnetic field by nature is going to have this kind of shape. Once there is magnetic field here, there will be the magnetic field from the permanent magnet will have this shape. it tends to stretch itself. So once stretching itself is going to push this magnetic field up and this magnetic field down. So this is a kind of simple explanation to the force generated. Again, two magnetic field will cause force. One force, or there is a force on this conductor. This dark is a conductor, and this is another conductor. I mean, one is going in and the one is coming out. This is going to result in force from this side and force from this side, which means this coil going to rotate. This is going to rotate. This is the idea. So the rotation is going to be the rotation of this coil. This is the coil. When it rotates, the pointer is attached to it, so the pointer will rotate as well to cause what is known to us as a deflection. So this is called deflection force, the force generated due to the two magnetic fields called deflection force. Now the other force is the controlling force. Controlling force is a kind of force generated opposite to the original force to avoid the pointer from exceeding its limit. Like what I mean by that, if let us say the measurement or the reading supposed to come to this point, so we are expecting the pointer to come to this location. If we don't have the controlling force, due to the momentum of inertia, the pointer will exceed this point. So it's not going to give us a right reading. That's why we generate kind of force against the control force. That force is generated by the hairspring or the spring, which made of wire like hair. It's very thin wire. That's why we call it hairspring sometimes. So that spring is going to, once the pointer start rotating, when the pointer starts its rotation, the spring will be squeezed somehow to store some energy in it. So some energy will be stored in the spring, which acting like force against the deflection force. If you look here, this is the deflection force, which pushing the pointer to this direction, and there will be a force generated by the spring, which will be on opposite direction. So we call this is controlling force. Again, mainly the controlling force is to carry the pointer without exceeding the point. Carry the pointer to the point of measurement, not exceeding the point of measurement. Usually the question will come here to ask what is the source of controlling force. So the source of controlling force is the spring. If I ask what is the function of the spring in DRC Novel or in the PMMC, it's to generate the controlling force which against the deflection force. It's generating controlling force which against the deflection force to keep the pointer flowing or moving until the right position, not to exceed the right position. The third force is the damping force. Damping force is going to be moving the pointer without oscillation. What is the meaning of that? You know, if you notice what I mentioned in the previous slide, we may get the pointer move starting from, let's say we want the pointer to come to this position. So if I say the pointer is oscillating, means it's going to go to left, then right, then left, then right, until it's stopped at the right position. Again, the pointer is supposed to come from this position here. It's supposed to stop here, but it will not stop. It will exceed up to here. Then it will come back 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 up to the middle. So this is called oscillation. If I draw a curve showing this operation, I will find that the curve is running starting from 0 and moving until certain point. It's not the right position, so it will drop. It's not the right position, it will go up. So we call this process oscillation until the pointer get to the steady state. Now this is going to take time in the measurement. It's not a problem, but it's going to make the measurement long. I have to wait until the pointer is stopped at the right position. To avoid that, we are going to depend on what is called damping force. Damping force is minimizing the oscillation. Now, how the damping force is to be generated, where from, what is the source of damping force? It's going to be what is known as eddy current. Eddy current is a current flowing in the core due to the magnetic field surrounding it. And the current is going to flow in a closed path inside the core. If I assume this is the core is metallic, so the metallic element in a magnetic field will get current induced in it, and the current going to have a closed path within the metallic part. So this is called eddy current. The eddy current going to cause kind of magnetic field. There will be magnetic field generated out of this current. This magnetic field, we don't want to solve it. We don't want to remove it. We like it. Usually, this kind of magnetic field, we try to remove it or avoid it or clear it. But in this kind of application, we want it because it's going to create kind of force which will damp the movement or the deflection of the pointer. So instead of the pointer going this way, let me try to clarify it. The pointer is starting at certain position. So let us say the pointer is supposed to come at this point. So if there is no eddy current and no magnetic field come of the eddy current, the pointer will start this way. It's going to go, then come back, then back, then back, until finally it's going to stop at its point, at this point. So finally it will stop at this point, but it will take time. To avoid this, or this is going to be minimized by the presence of eddy current, so it's going to look like this. If it's at this position, I want it to come here, it's going to start and come. I mean, it's going to be very short oscillation. So it will start, go exceed the position, then come back and finish. That's it. So this is going to be faster in terms of getting the right measurement. Now we need to calculate the torque which generated in the PMMC, the torque created in the PMMC. We will go direct to the equation which will generate it. The torque, we call it deflection torque, TD. It's calculated by these parameters. It's equal to B into A into I into N, where B is the flux density in the core. Let me clarify here, we are having permanent magnet. Inside the permanent magnet, there is a cylinder. There is a cylinder where on the cylinder there is a coil. We agreed just now that there will be magnetic field due to the current flowing in the coil and another magnetic field due to the permanent magnet. Both of them are going to cause what is known as the deflection. So the pointer will start. Now, how to calculate the torque which will move the pointer? It's to be calculated by this parameter, where B is the magnetic field. B is the flux density in the air gap. The magnetic field means the magnetic field created by the permanent magnet. And A is the effective coil area. This coil, the red color is the coil. So the red color, I am looking at it from the top view. This is the top view of the operation. If I look at it from this kind of view, side view, it's going to look like this. This is the coil. So this is the coil, where this is one terminal of the coil and this is the other terminal. When I look at the effective coil area, that means the area of this part, area of this piece, because it's going to give me the dimension of the wire. That's why we like to get the area, because the area is giving me the dimension of the wire which having current flowing in it. N is the number of turn for this coil. How many turn? Turn means this is 1 turn, 2 turns, 3 turns, and so on. I is the current flowing in it. I is the current flowing in the coil. So this is the coil. As I said, this is the coil. The coil is having 2 terminals. This current flowing in the coil is known as I.